Hello and welcome to another edition of Finance Titbits. For those of us who may wonder whether the zero and constant growth stock valuation formulae fell from the sky, or were dug up in some excavation, or whether they appeared as an inspiration in a dream, this brief video should cure the wonder and establish some logic. Common stock valuation is something that we commonly learn in introductory finance modules. And for dividend paying companies, we attempt a myriad questions where the dividend either stays the same or grows at a constant rate over time. Now, if the dividend remains constant, we simply express the stock price as the discounted value of a perpetual stream of dividends which stay the same. For example, if we said that P0 represented the stock price, the letter D represented the dividend per share, and the investors demanded a rate of return, I don't know, maybe something called K, then we could specify P0 as per our textbooks, and that would be equal to the stream of dividends divided by the required rate of return, which acts as our discount rate. And this is what you call the zero growth model, right? So let's just label it as the zero growth model, which we are aware of. That in such a case, P0 is equal to D over K is not because somebody whispered the formula to the textbook authors. It is a result actually of recognizing a few things. For example, we need to recognize that the price of a dividend paying stock is, among other things, the function of future expected dividends. So I'm just writing D for expected dividends here. And another thing that comes to mind is that since future needs discounting to arrive at its present worth, we discount each future expected dividend and then add all individual present values to know the current value of the stock. So if I were to write that out in an equation format, we would say that P0 would be simply the present value of the dividend at time one. Then we will add present value of the dividend received in time two, and then we will add present value of dividend received in time three, and so on this series would go. If we were to express this idea more formally, we would say that P0 would be equal to, so instead of writing PV of D1 here, we could say D1, D over, because I'm not going to distinguish between D1, D2, and D3. These 1, 2, and 3, these digits simply represent the time period that the dividend is being received in. It is not representing the amount of dividend because by definition in the zero growth model, the dividend is constant anyway. So basically then we are writing D over 1 plus K for the first term, and then we are writing the second term D over 1 plus K raised to the power of 2, and then we are saying D over 1 plus K raised to the power of 3, and so on this series goes. At number 3, we see the problem. So let's note down the problem at number 3. The problem is that since common stocks do not have a defined tenure, the future, well, because you saw here that I left the series open, so it could go on to any length of time. So, because common stocks don't have a defined tenure, as I said, the future can extend to infinity, and we will need to keep adding the term forever as follows. So, we will say P0 is equal to D over 1 plus K. We will say then plus D over 1 plus K to the power 2. We will say then add to this D over 1 plus K raised to the power of 3, and so on. This will go till the end of time, right? So because who knows till what time the company is going to go on, unless, of course, formally or legally shut down or wound up in the case of a liquidation or some event of that sort. So, but this is torture. How long can you keep adding the terms? You would never arrive at the answer. So at number 4, we can maybe start thinking of a solution, which would be that to avoid adding the terms forever, we can first of all do one thing, and that is that we can write this P0 equation a little bit more concisely by realizing that the right-hand side of the equation is a series of additions. So there's a plus sign, there's a plus sign, there's a plus sign, there's a plus sign. So we are constantly adding one term to the next. And this operation of addition goes on till infinity. So we can say that we are adding by just invoking the sum sign. We are adding, we're starting at time 1 and we are going on till infinity, and we keep adding this term d over 1 plus k raised to the power of time, which can range from 1 to infinity, so raised to the power of t. So once we have shortened this out, we can try and rewrite it as maybe this formulation t varying from 1 to infinity. We take a sum of d multiplied by 1 over 1 plus k to the power of t, right? That doesn't really make a difference. This tells us that each successive term in the series now grows by a common ratio, if you realize that. We can identify a common ratio. Let's see how. A common ratio is going to be 1 over 1 plus k. Because if you look at the first term, here, and let's rewrite it at the bottom here, d over 1 plus k is equal to, so I'm writing this in the newer format now, d multiplied by 1 over k, right? So if this is my first term, then the second term, which is this guy here, second term, I can write that as maybe d multiplied by 1 over 1 plus k multiplied by 1 over 1 plus k, right? So when I moved on to the second term, I multiplied with a ratio 1 over 1 plus k. So that is how it gave me d multiplied by 1 over 1 plus k to the power 2, which became then equal to d over 1 plus k raised to the power 2. So if I had to write out the third term, I would have written d times, this exists from before, 1 over 1 plus k times 1 over 1 plus k. And then for the third term, I would multiply with another 1 over 1 plus k. So what we are seeing is that as we progress ahead in time, we continue to multiply with a common ratio, which is nothing but 1 over 1 plus k. So that is one observation that we have made. So likewise, we could write out all other terms in this manner using the common ratio. So basically, if we were to summarize this, what we have on our hands is the sum of, what we have is sum of an infinite geometric series, right? Which fortunately can be computed very easily by writing the sum of an infinite geometric series formula. So if I say S represents the sum of an infinite geometric series, then that is equal to A over 1 minus R, where, folks, A stands for the first term in the series. So I'm just saying this is the first term in the series, and R is the common ratio, which we have seen earlier in our context is 1 over 1 plus k. So if we substitute these items where they belong, what we are going to see is that P0 is simply a sum of the geometric series, this S, which is further defined as this. So let's write this definition at this point. So we write our A first, which is, let's define A. What is the first term? We can go back and see what's the first term. The first term is this guy here, d over 1 plus k, or we can take up this formulation d times 1 over 1 plus k. So let's write that out here. The first term is d multiplied by 1 over 1 plus k. And then we need to divide this whole stuff by 1 minus the common ratio, which is 1 over 1 plus k. And the rest is simply a simplification of this item. So let's say on the numerator we have d over 1 plus k. And in the denominator we can just solve this out. we will have 1 plus k minus 1 divided by 1 plus k. So what do we see here? We see that there's a 1 plus k here in the denominator, and there's a 1 plus k here in the denominator. They are going to cancel out. There's a plus 1 here and there's a minus 1 here. They are going to cancel out, and that is going to leave us with only the d in the numerator and only the k, which is here in the denominator. So what we have with us here is P0 is equal to d over k, which is the zero growth formula that we read in the textbooks. Isn't that cool? So then continuing this in the same vein, what if say the dividend was growing now? The dividend was growing. So if the dividend grows at a constant rate, and let's give it a name, say G, then we would write P0 as, and I will be quiet and do the math here. You keep looking at the various steps.